This next video will discuss section 8.2, solids and liquids, but also section 8.3, gases and pressures. So gases are characterized by several features. The shape of a gas is simply that of its container. That is, gases adapt to the shape of their container. Gases will also fill whatever container they are placed in. We often will say that gases have variable volume. Because there is a lot of space between particles that make up a gas, we note that gases can be readily compressed. For similar reasons, we'll note that gases have pretty low densities because, well, there's a lot of empty space between particles. And as gases can be compressed, their density can be changed. So if I apply a pressure to a gas, that's going to squash the particles closer together and the gas will become more dense. So what we really want to note about gases is that they have this property of variable volume and also variable shape. In liquids, the particles that make up the sample are a lot closer together than what they are in gases. In fact, they're touching and the particles are not moving around as much. Because the particles are a lot closer to one another in a liquid than they are in a gas, the density of liquids is much greater than that of a gas. And if you think about it, a water balloon weighs a lot more than a balloon that's filled with a gas, such as air, of the same volume. Water balloons are pretty weighty. The density of a liquid is fixed because, well, you can't really push the particles much closer together than what they already are. While liquids do adapt to the shape of the container in which they are placed, they have a fixed volume. The volume being fixed is helpful because that means that we can use things like a measuring cup to measure out the volume of a liquid. When we pour it to another container, we're confident that it contains or that it maintains the same volume. Because the particles in a liquid are really close to one another, liquids are not easily compressed. In a solid, the particles that make up the sample of matter are very close to one another and most commonly in a very orderly arrangement. This gives rise to a high density and also means that solids are not easily compressed because, well, there just isn't a lot of space between the particles. Solids have a shape, density, and volume that is fixed. The shape of a solid does not depend on the shape of its container. The volume of a solid does not depend on the volume of its container. As the volume of a sample of a solid is fixed, that also means that the density of a sample of a solid is also fixed. So here's an example problem from the book. It says, in which state or states of matter does each statement describe? It says this state has a definite or unchanging volume, and that applies to both liquids and solids. Gases are the only state of matter that have a variable volume. It says this state has no definite shape. Well, that applies to liquids and it also applies to gases. Those things just adapt to the shape of the container that they are placed in. And C, it says this state allows the individual particles to move about while remaining in contact. Well, there are two states of matter in which the particles are in contact, solid and liquid, but only in the liquid are the particles able to move about. So this state is referring to the liquid state, or this statement is referring to the liquid state. Okay, here's a similar question with some different phrases to evaluate. This state has individual particles in a fixed position with regard to each other, and this relates to solids. In solids, The particles are organized in an orderly, repeating fashion, and the particles can not really move much around at all. This state has individual particles far apart from each other in space. This refers to the gaseous state, so we can say gases. Only in gases are the particles far apart from each other. And this state has a definite shape that refers to solids. Both liquids and gases adapt to the shape of their container. Okay, so section 8.3 is concerned with gases and pressures. So a powerful model for describing the behavior of gases is the kinetic theory of gases. This is built around 4 key ideas. Gases are composed of tiny particles, which nowadays we would describe as either being atoms or molecules, that are separated by large distances. Gas particles are constantly moving and experiencing collisions with other gas particles and the walls of their container. Okay, we've already kind of said that before, haven't we? This is a little bit new. The velocity or speed of the gas particles is related to the temperature of a gas, and in particular, that as the temperature goes up, the velocity of our gas particles will go up. And then this last point might seem non-obvious. We're going to assume that gas particles do not experience any force of attraction or repulsion with each other. That is, there are no intermolecular forces between gas particles. Because gas particles are constantly colliding with their container walls, this means that a gas will exert a force or pressure on its container walls. So how are we going to measure this pressure? Well, there's a device called the barometer that was originally intended to measure atmospheric pressure. This was devised by a guy called Evangelista Torricelli in the 17th century, and he was a student of Galileo. And what Torricelli did was he took a 1 meter glass test tube, he filled it with mercury, he put his thumb over one end, he turned it upside down, stuck his whole hand into a dish of mercury, and pulled his finger away. And somewhat surprisingly, a little bit of the mercury flowed out, but not all of it. In fact, most of the mercury remained in the tube. So only 240 millimeters out of 1,000 millimeters flowed out into the dish of mercury. So imagine what would have happened if we did this experiment without sticking the end of the tube in the dish of mercury first. Well, we would have ended up with mercury all over the floor. What's holding the mercury in the tube is the force of the air pressing down on the mercury in the dish, and that exerts a force which can support the column of mercury 760 millimeters high. So for this reason, commonly in chemistry, pressure is expressed in torr, and 1 torr is exactly the same as 1 millimeter of mercury. A standard atmosphere has a pressure of 760 millimeters of mercury, or 760 torr. If you want to put that into more familiar units, this is 14.7 psi, or about half the pressure in your car tires. In the international system of units, and in particular in the metric system, pressure is sometimes expressed in pascals, and there is 1.013 by 10 to the 5 pascals in 760 millimeters of mercury. Now, you don't need to remember all of these conversion factors, but if you are given these conversion factors, you should be able to perform unit conversions between different systems of pressure. So let's have a look at this. It says write a conversion factor to determine how many atmospheres are in 1,547 millimeters of mercury. So 1,547 millimeters of mercury, and we're going to need to multiply by a conversion factor that has atmospheres on the top row and millimeters of mercury on the bottom. And what I know is that in 1 atmosphere there are 760 millimeters of mercury, and so there is our conversion factor. The next one says, write a conversion factor to determine how many millimeters of mercury are in 9.65 atm or atmospheres. So 9.65 atmospheres, and we have to multiply by a conversion factor that has millimeters of mercury on the top line and atmospheres on the bottom. And we just learned there are 760 millimeters of mercury in 1 atm. So there is our conversion factor. Okay, and that concludes our section on gases and pressures.